Introduction to Light, lecture number 1. So we're going to start this semester talking about the atom again, but in a little more detail. I want to talk about it sort of instead of focusing on protons and electrons like we did last semester, we're going to talk about neutrons, the nucleus. We're going to talk more about the electrons and the interaction of those electrons in this. In order to do that, we're going to look at movement of electrons, and to do that, we're going to look more closely at light. So this lecture is going to focus primarily on light and light's interaction with the atom. So the first thing we have to understand is the properties of a wave. So a wave is defined as the vibrating disturbance by which energy is transmitted. So we have this energy that's being transmitted through space in the form of a wave. And there's 3 properties that we need to know about for each wave. The first is this wavelength. It's the wavelength, which is defined by this lambda symbol, is the distance between 2 identical points on successive waves. So we can think of it as peak to peak or trough to trough. That's sort of the most common way to picture the wavelength. But any 2 identical points, as it's going up or going down, it doesn't matter. 2 identical points. That distance between those points is defined as the wavelength. The amplitude is the vertical distance from the midline of the wave from either its peak to its trough. So it's sort of how big that wave is. So we're not going to talk too much about the amplitude of a wave in this course, but I just want you to be aware of it. It does have an effect on what we'll talk about later, but it's sort of not as obvious. Okay. The third property is this frequency, which is symbolized by this Greek symbol nu, this V sort of. So it's the number of waves that pass a successive point in 1 second, which is defined as a hertz. So 1 wavelength through, or 1 cycle per second, is a hertz, capital H-Z. Right, so we can think about this seagull sitting on the ocean as it goes up and down, bobs as many times as waves pass by that seagull, and unit time is the frequency. So we can talk about the speed of any wave then being the number of the wavelength of that wave times the frequency that it's traveling. So it's going to relate to the speed. So wavelength times frequency. And so these are just general properties of waves. What we're talking primarily about now is light, or what we call electromagnetic radiation. So light, or electromagnetic radiation, has 2 components to it. It has an electric field component and a magnetic field component. And those are perpendicular from each other, as you can see in this diagram. And it's this form of energy transmission we think of as light. And Maxwell in 1873 proposed that light that we see is an actual function of these electromagnetic waves. Therefore, we can talk about all light as having the speed of that light as being from this wavelength times the frequency is equal to the speed of light. And we calculated it later to be about 3.0 times 10 to the 8th meters per second. So if we know the frequency of a wave, and the speed of light, since that's a constant, all this electromagnetic radiation always has this speed. If we know those 2 values, we can then calculate the third. So using this, the speed of light plus the frequency of the wavelength, we can calculate the other one. Right? And we can think about, as it's shown here, all of this is the sort of the full spectrum of electromagnetic radiation. At the bottom here, we see visible light, which goes from about 400 nanometers to about 700 nanometers. Very sort of, the exact range is dependent on each person, their ability to pick up light. Some people have a little broader spectrum, some a little narrower. But typically it's about from 400 to 700 nanometers. Right? But you can see here on this, it's a very small portion of the entire electromagnetic spectrum. If we go one direction, we go to the ultraviolet. If we go the other, we go to infrared, and then microwave radios, and sort of as it spreads off there. Not really concerned that you know all of these different, the order that these are in. Just be aware that they are all different spectrums of electromagnetic radiation or light. So now let's talk a little bit about how this comes into play in far as chemistry when we're talking about atoms. Planck was doing some experiments where he saw that he could shine light on an object and get energy transitions to occur. Or he can add energy to objects, atoms, and get light to come out. Right? And during his experiments, he came up with this hypothesis, or this theory, that atoms could emit or absorb energy only in discrete quantities, which he called quantum, or quanta, the plural. Right? So the amount of energy that these atoms can absorb or release is defined by only a certain amount. So there's these different levels of energy that can be absorbed or emitted. Right? And this quantum is the smallest quantity of energy that can be emitted or absorbed in the form of electromagnetic radiation. Therefore, we can then take this amount of energy and relate it to the wave through this constant. So the energy of light is equal to Planck's constant h times the frequency. We can combine that with our other equation to relate the energy versus wavelength if we wish, and we'll do those calculations later. But we're now relating the energy to these properties of the waves through Planck's constant, which is 6.63 or 6.626 times 10 to the negative 34th joules times seconds. Right, so now we can relate the wavelength, the frequency, and the energy of a wave or light through these properties. So if we know one, we can talk about the other. And we'll see, as you saw before, as the wavelength got smaller, this energy then the frequency gets higher, which means that the energy is going to get higher as well. So the wavelength and the frequency are inversely proportional to each other, and energy is, as frequency goes up, energy goes up. Conversely, as wavelength goes down, energy goes up. But let's talk a little bit more about how this has to do with atoms and chemistry. So what we can do is, if we take this gas of a single atom, or single element, and we add energy to it through, say, like a light bulb, a neon lights, that's what you do, and you fill a tube with neon and you excite it with electricity. We see that we get light out. If we then separate this light, we see that we don't get a continuous spectrum. We get what we call line spectra, as you can see in the figure here. Right? This is for the hydrogen atom. If we excite hydrogen gas, we get these line spectra out. And it's these line spectra which give evidence to this idea of quantization. Right? That there's only a certain amount, these wavelengths of light correspond to certain energy changes within the atom. Right? If we go back to Bohr's theory of an atom, where we have this nucleus, and around this nucleus we have those electrons, we can then relate this quantization of light, this absorption or emission of light from the atom, based on these energy levels. Right? So we can say that the electron can exist in certain distances from the nucleus, or certain energy levels. And we can get the electron to move from one energy level to another by adding a specific amount of energy. Right? Or if it falls from a higher energy level to a lower energy level, the amount of energy that comes out in the form of light is dependent on the different distance between those energy levels. Right? Where the lowest energy level is what we call the ground state, the highest energy level is the excited state, or higher energy levels. And we can then relate the energy of these levels using this equation here, where the energy of a certain level is equal to a negative HR, HR is a Reinberg constant, times 1 over the energy level, the Princeton quantum number, a whole number. We'll talk about exactly what that means in the next lecture, but squared. Right? And the Reinberg constant is 2.18 times 10 to the negative 14 joules. Right? So then if we look at the hydrogen atom, we can see that we get these distinct energy changes corresponding to lines, depending on their energy level. So if we have an electron fall from, say, energy level 3 down to energy level 2, that's going to give us a red light. Right? The energy of that transition is going to be related to give us light in that wavelength of red. And we can do calculations for this. We can take the energy change, this delta E is the final energy level minus the initial energy level, where both of those energy levels are defined by this Reinberg equation, so that we can say that this delta E is equal to the Reinberg constant times 1 over the initial energy level squared minus 1 over the final energy level squared. And we can do those calculations to predict, based on these energy level changes, what's going to happen and what spectrum of light we have. We've named these different series for the hydrogen atom. Again, you should be able to do this calculation. You don't necessarily need to know that transitions to the first level are always the Lyman series or whatever. That's not as important. Just be able to do this calculation.